In this video, I'm going to explain how you can use calorimetry, or that heat equation, to measure the heat of a reaction. So you need to be comfortable with that equation, Q equals M times C times delta T, because we're going to be using that heat transfer equation to measure how much energy is released or absorbed in a reaction. Now, we need a device to put the reaction in. So we're going to use a Coffee Cup Calorimeter, which is kind of a crude looking device, but it does a good job measuring the amount of energy released or absorbed in a chemical reaction. So this Coffee Cup Calorimeter has two coffee cups that are nested in each other, and this is what provides the insulation so that no heat or very little heat from the environment is transferred. So we have those styrofoam cups, we have a thermometer, we have a glass stirring rod, and don't tell anyone, sometimes I use my thermometer to stir a little bit if you don't have both, or if you don't have room for both or holes for both. Then we have a cork lid or some sort of thick insulated lid, but we want it to be loose fitting. And the reason we want it to be loose fitting is because if there's any buildup of gas during a chemical reaction, we want the gas to be able to escape, because we don't want any pressure to build up, because we don't want any work to be done. We want to just eliminate work out of that enthalpy equation. So we can just figure out enthalpy by using Q. So this is the device, and we're going to allow reactions to be performed in this device, and we're going to use water as the thing that absorbs the reaction, the heat from the reaction, or provides the energy if a reaction is cooling. So we're going to take a look at some practice problems. If we're asked to mix 20 milliliters of a 1 molar HCl solution with 100 milliliters of a 1.0 molar NaOH solution, the initial temperature of both solutions, and remember they're in water, is 18.9 degrees Celsius. The temperature of the final solution is 21.1 degrees Celsius, so there was some heat evolved here. Assume that HCl and NaOH have the same specific heat capacity and density as water, because both of them are in water solutions. What is the change in heat? And then we're going to go on and calculate the molar heat of neutralization. Now you might have noticed the first thing that I did is I wrote out the equation for what the process that is happening. If you know this information, write it down. Now these are two reactants in an aqueous solution. So they're actually going to be in the water that will be heated or cooled as they react together, as the acid and the base react together. So we're going to use that Q equals M times C times delta T. And we're going to measure how much energy the water gets from this reaction. So we need to know the mass of the water, and everything is going to be based on the water for the purposes of this calculation. Now the mass of the water, we have 20 milliliters and 100 milliliters of water. In order to figure out the mass of this, you need to know the density of water and the density of these solutions. And we said in the problem here that the density of the solutions is going to be the same as the density of water, and 1 milliliter of water is equal to 1 gram. So if we have 20 and 100 milliliters of solution, we basically have what we can assume to be close to 120 grams of water that can be absorbing or releasing energy to this reaction. So the mass of the water is 120 grams. So remember, for this problem, everything is focused on how much the water is gaining or losing. The specific heat capacity of water is 4.184 joules per gram degree Celsius, and the change in temperature of the water is 21.1 is our final minus our initial 18.9 degrees Celsius. That gives us 2.2 degrees Celsius. The water is heating up. And the overall amount of energy that the water is gaining is found by taking 120. By the way, I want to show you that I'm canceling out grams and degrees Celsius. So I have 120 times 4.184 times 2.2. And the unit that will remain is going to be joules. So my answer is, and we'll round this to two significant figures. The calculator gives me 1,104.6 joules, and I'm going to round that so I get 1,100 joules. That's how much the water is gaining. which means that the reaction, and what we care about is the heat of reaction or the energy of the reaction. That means the reaction is losing that energy. So the reaction is going to be the opposite of that. Remember, the Q lost equals the Q gained. So the reaction is going to be negative 1,100 joules. So we're just going to be focusing on the reaction. Remember, the water is how we measure the reaction. This isn't the end of the problem. What we want to do then is calculate the molar heat of neutralization. In order to do this, and we want joules per mole or kilojoules per mole for this, what we want to do is we want to figure out how many moles are reacting. So we have solutions. We have a volume and we have a molarity of a solution. Remember, if we want to figure out the number of moles, we take the molarity times the volume of that solution. So the number of moles of hydrochloric acid is 0.020. And the number of moles of the base, the sodium hydroxide, is 0.100 moles. So we have 0.02 versus 0.1. This becomes a limiting reactant problem. The 0.02 is the limiting reactant. So not all of the base will react, only 0.02 moles of each because it's a 1-to-1 ratio. So that's the quantity of moles that we will use for this reaction. And the delta H is going to be, remember, in kilojoules or joules per mole. So the number of joules, negative 1,100 joules, divided by the number of moles reacting, 0.020 moles. And if we calculate this all out, we get negative 55,000 joules per mole. And I'm actually going to convert this to kilojoules per mole. So negative 55,000 joules per mole is actually equal to negative 55 kilojoules per mole because 1 kilojoule is equal to 1,000 joules. So negative 55 kilojoules per mole. For this. So our answer for the molar heat of neutralization, because this is a neutralization reaction, is negative 55 kilojoules per mole. And we used water to measure how much energy was being given off by this neutralization because the water heated up, which meant that the reaction was releasing energy. It was an exothermic reaction. All right, so next question. When 1.34 grams of potassium bromide dissolves in 74 grams of water in a coffee cup calorimeter, the temperature of the water drops from 18.000 degrees Celsius to 17.279 degrees Celsius. We want to determine the delta H for dissolving 1 mole of KBr. So the heat of solution is actually what we're looking for. And the reaction for the solution is written out as KBr gives us potassium ions and bromide ions. So we're going to write out our equation, Q equals MC delta T, and we're always going to be focused on the water that is gaining or losing the energy from this. So we have 74.0 grams of water. The specific heat capacity of water is 4.184 joules per gram degrees Celsius. And the temperature change of the water is final minus initial. So 17.279 minus 18.000, our initial water temperature. So the water decreased in temperature. The water got colder. So it got colder by 0.721. So we write a negative 0.721 degrees Celsius. So if I want to find out how much water or how much energy the water lost to this reaction, how much it cooled, how much energy the water lost to this reaction, we have 74 times 4.184 times negative 0.721, and the degrees Celsius and the grams cancel out, giving us joules. And we're getting a negative number for the water here. So we have negative 223 joules. That's the water. Now the solution, as it becomes a solution, is going to be the one that's causing the water to lose the temperature, lose that heat. So the amount of energy that the water loses is equal to the amount of energy that the solution gains, you could say. So it's the opposite. Q lost equals negative Q gained. So if we're looking at that dissolution or solution energy, the dissolving energy, we get a positive 223 joules. And that means that this is an endothermic reaction. If it's positive, it's endothermic, meaning it's absorbing energy. And it's absorbing that energy from the water because the water is losing energy. So the dissolving energy is 223 joules. Now, the second part of this question is saying determine the delta H for dissolving 1 mole of this KBr. So we need to know how many moles we have. Our delta H, or delta H of solution, is going to be equal to joules per mole or kilojoules per mole. And we have 223 joules, but the amount of grams of KBr is 1.34. So we have 1.34 grams of KBr. Now you guys all should know really, really well how to convert grams to moles, and that's what we're going to do here. We're going to cancel out grams and we're going to turn it into moles. So we have grams of KBr turning into moles of KBr. And we have to use our periodic tables to figure this out. 1 mole of potassium bromide is equal to 119 grams of potassium bromide. So I'm going to take my 223 joules over grams of KBr, and my grams of KBr will cancel out, giving me 223 times 119, which equals 19,800 joules, and that's over moles, joules per mole. And I'm actually going to convert this to kilojoules per mole, so 19.8 kilojoules per mole for my answer for this question. That's the molar heat of solution, 19.8 kilojoules per mole.